Okay. Okay, so we'll begin. So the last time we looked at fundamental subspaces and we started discussing the rank. Today we will finish the discussion about the rank of a matrix and then move on to the inner product and the Gram-Schmidt orthogonalization process. So before we begin, there are a few announcements to make. The first is that homework 1 is online. So please look at it and start solving it already. The homeworks, so in addition, so these homeworks are not due. You do not need to turn them in. Okay. However, we will have assignments, and assignments will typically be one of the problems in the homework, and we will assign the we will offer the assignments, or they will be available to you at 5 p.m. on Mondays, and they're due by 8 p.m. Now the idea is that these assignments should take you no more than half an hour or 45 minutes to solve, and so you have plenty of time to complete the assignment and submit it. But this 8 p.m. is a hard deadline. Late submissions will not be entertained, so you'll have to solve it and submit it by 8 p.m. The assignment itself will be closely related to the homework problems. For example, we may even just copy and paste one of the homework problems, and that will be your assignment. Just to make sure that the process works out okay, we'll have a simple practice assignment this Wednesday. So look out for the assignment at 5 p.m. and you'll have to submit it by 8 p.m. So this is not due, or not part of your evaluation. But just to kind of understand the process of finding your assignment and then solving it and uploading your solution. Now, if there is something to write out that you write out in your book and you need to scan and upload it, normally what I do is I use this app called Adobe Scan. That app allows you to take a picture of your notebook and it saves it as a PDF file, and then you can email that to yourself, download it onto your computer, and then insert it as part of your solution to the assignment. Now in Teams, when you try to insert a file, it gives you two options: insert file and insert file printout. Please select insert file printout. So while inserting files, not insert file. The reason is that if you say insert file printout, it will display the PDF right there, and that makes it easy for the assignment to be evaluated. Otherwise, it's only available for download, and we won't be able to insert our comments on that and then upload it back. It's much more effort for us, and with a class of almost 130 students, we won't evaluate files which are inserted as file. We'll only evaluate the ones that are inserted as file printout. We have to be a bit systematic for a class this size, otherwise it will become very difficult to manage. Any questions about these announcements?
Sir, today there will be no assignments, right?
No assignment today because I only assigned the homework now. So you will need some time to look at the homework and start solving them. So your first formal assignment will be next Monday, but we'll just have a practice assignment this Wednesday.
Okay, sir. And sir, when homeworks will be posted, which days?
Typically once in 2 weeks or so, maybe once a week sometimes.
Okay, sir.
But you will have about a week or so to look at the homework and it before it is due, before we give an assignment on it.
Okay, sir. Thank you.
Okay.
Sir. Yes.
So
There
the
is a
deadline,
question here.
if the assignment is given at 5 p.m. within 3 hours, 8 p.m. that's the deadline, or
Yes. Yes. So when the assignment is made available, it will also come with a deadline by which you have to submit it. Okay, and it will be 8 p.m. There was a question on the chat about whether auditing students need to submit assignments. My suggestion is auditing students, please don't submit your assignments. If you're very keen on figuring out whether you've solved the assignment correctly or not, please feel free to attend the TA session and you can ask the TA whether you answered the question correctly. There is enough administrative overhead with this course with the crediting students already. So we don't want to clutter that with assignments submitted by auditing students also. So auditing students need not submit, or please don't submit.
Excuse me, sir.
Yes.
Sir, where exactly are we supposed to upload the file? I did not quite understand that.
So the assignment will be offered in the assignment section of the Teams. And so when you get the assignment, you will have an option to insert your answers right there.
Okay.
So that is this is exactly the reason why we are having a practice assignment this Wednesday, so that you become familiar with the process of getting and answering an assignment.
Okay, sir. Thank you.
Okay. Any other questions? Okay, if not, we'll
Sir,
go ahead.
sir,
Yeah, go ahead.
sir, is these assessment assignments are similar to quizzes, sir? Means 24% of weightage is for these assignments.
Correct.
Okay, sir.
Same thing. Yes.
Okay, sir.
Yeah. So the last class we were discussing. Okay. By the way, for those of you who just joined the course and who didn't attend last week's lectures, I'll just show you some of the key pointers in Teams so that you are familiar with where what is. So if you go to Teams, in the posts, you can go back to the previous posts and see what people have posted. Just because the posts can get cluttered, I also have a separate channel for announcements. So key announcements will be posted here. And then you can go to files, and in files, not in announcements.
Different channels have different files.
Yeah. So you go to general and go to files. Then there is a class materials folder. And within the class materials folder, video lectures are here. So these are the previous video lectures that you may have missed. Textbooks are in this folder. Homeworks will be posted in this folder. And the class notes will be posted in this folder. Okay, so you will have access to all of them. Eventually, when you have assignments, they will appear here. Incidentally, if you go to class notebook, So this has several sections. There's a collaboration space where anybody can post whatever they like. There is also a content library, which I'm not using right now. I didn't want to use both the content library and the files to post content because it's going to be difficult for you to navigate and figure out where they are. Initially, for the trial purpose, I had uploaded 2 of the lecture notes in here, but you will not be using this per se. All the content will be posted under files. If there's a change to this, I'll let you know. Then each of you will have your own space. I'm just going to pick one student at random and show you what's going to be in that space. So here there are class notes, handouts, homework, and quizzes. And in the homework section, so we'll have to see. This is something new for me, but when an assignment is posted, it'll end up showing up somewhere here. And from that, we will be able to access your reply to the assignment and see how evaluate your answers. Okay. Okay, so let's continue. So we were talking about the rank. The basic definition is that the rank of a matrix A is the dimension of the range space of A. And the dimension itself is the number of vectors in a basis for a vector space. And the range space of A is the span of the columns of A, and that is a vector space. And the dimension of that vector space is the rank of a matrix. So the last time we saw that rank is equal to the number of linearly independent columns in A. And there is a remarkable fact, which is that the rank of A equals the rank of A transpose, row rank equals column rank. Then we also said that if you're given a linear system of equations Ax equals B, it can have no solution, one solution, or infinitely many solutions. And it will have at least one solution if the rank of the augmented matrix AB equals the rank of A. If the rank of the augmented matrix A concatenated with B is greater than the rank of A, then there is no solution. Then we said that it's possible to find a row reduced echelon form for a matrix. And you do this by performing row operations. And these row operations or elementary row operations, there are 3 of them. The first is to exchange a pair of rows. The second is to multiply a row by a non-zero scalar. And the third is adding a scalar multiple of one row to another row. So none of these operations change the rank, and therefore if you look at the row reduced echelon form and if you can find out the rank of the row reduced echelon form, then that tells you the rank of the original matrix. And the row reduced echelon form is in such a way that the diagonal entries will be non-zero up to a point, and then you have all 0 rows. And the number of non-zero rows in the row reduced echelon form is the rank of the matrix. So it's important to remember that the rank of the matrix is the number of non-zero rows in the row reduced echelon form. I often find students saying that the rank of the matrix is the number of non-zeros in the row reduced echelon form. That is incorrect. It's not the number of non-zero elements in the row reduced echelon form. It is the number of non-zero rows in the row reduced echelon form. Okay, so those were the properties we saw the last time. Now I did not actually walk you through how to find the row reduced echelon form of a matrix, but I assume that this is something that you have seen in your undergraduate linear algebra. So if you've forgotten how to find the row reduced echelon form of a matrix, you should just practice it. You should look it up and then practice it on 1 or 2 matrices to make sure you're aware of how to do it. So we'll continue with these properties. The next property is that if the rank of A is R, then exactly R columns of A are linearly independent. And exactly are rows of A are linearly independent. Also, there is an R cross R submatrix of this matrix A, which has a non-zero determinant. So there are two keywords that I've dropped here. One is a submatrix and the other is a determinant. So the submatrix of a matrix is obtained by, so you pick R rows of the matrix A and you pick R columns of the matrix. When you do this, if you select the elements that are defined by these R rows and R columns, that gives you an R cross R submatrix of the matrix. So for instance, if I take a matrix 1, 2, 7, 6, 2, 3, 8, 9, 7, 2, 1, 4, and if I take rows 2 and 3 and columns say 3 and 4, then I get a 2 cross 2 submatrix. Eight, 1, 9, and 4. So there is an R cross R submatrix of A with non-zero determinant, and determinant is something that I have not defined yet. You might remember it from your undergraduate program, but we will also study it in more detail later in the course. But more importantly, and all R plus 1 cross R plus 1 submatrices have zero determinant. Another obvious property is that the rank cannot increase by deleting rows or columns. And similarly, rank cannot decrease by adding rows or columns. Okay, because when you add rows or columns, you can only increase the span or the dimension of the span of the columns of the matrix, and so the rank cannot decrease if you add a row or a column to the matrix. The next question is, what happens to the rank of a matrix, pair of matrices, when you add or multiply them? And so there are some inequalities. In general, you can't say something, you cannot give a universal answer to the rank of a matrix when you add two matrices or you multiply two matrices, but you can give some inequalities. So for example, if I have A in R to the M cross K and B in R to the K cross N, so that AB is well defined, A times B, then we have that rank of A plus rank of B minus K is less than or equal to rank of AB is less than or equal to min of rank A, rank B. So in other words, you cannot increase the rank of a matrix by multiplying it by some other matrix B, its rank is at most rank of A. Similarly, you cannot increase the rank of a matrix B by pre-multiplying it by another matrix A. Its rank is at most rank of B. So one other way to see this is that, for example, if Bx is equal to 0, then ABx is also obviously equal to 0. So that any vector which lies in the null space of B also lies in the null space of AB. And so we can say that the dimension of the null space of AB is at least equal to the dimension of the null space of B, which implies, remember now the rank nullity theorem, the dimension of the null space of AB and the rank of A should add up to the value m or n. Okay, so so that means that the rank of AB is less than or equal to rank of B. Similarly, you can make an argument in terms of if Y transpose A equal to 0, then Y transpose AB equals 0, and so it goes. Another well-known inequality is the Sylvester inequality. Which says that this is about adding matrices. So it says that mod of rank A minus rank B is less than or equal to rank of A plus B is less than or equal to rank A plus rank B. See, one way to get some intuition into these inequalities is to try to think about simple matrices that you can construct where each of these inequalities are satisfied with equality. Okay. So for example, this inequality, this first part, this is satisfied with equality if and only if range space of A intersection range space of B is the zero vector, and range space of A transpose, or the range of the rows of A intersection span of the columns of B transpose is the zero vector. Now the Sylvester inequality is actually the special case of another inequality. Okay, there's one other small remark I want to make. This inequality here, rank of A plus B is less than or equal to rank A plus rank B. I'll draw a star here and make a remark on it. So this is called the subadditivity property of the rank, and the consequence of this is that any rank K matrix can be written as the sum of K rank 1 matrices, but not fewer. So you can't write a rank K matrix as the sum of fewer than K rank 1 matrices. So this, as I was going to say, this Sylvester inequality is a special case of more general inequality called Frobenius inequality. Which says that if you have A in R to the M cross K and B in R to the K cross P and C in R to the P cross N, then rank of AB plus rank of BC is less than or equal to rank of P plus rank of ABC with equality if and only if there exist matrices X and Y of appropriate dimension such that B can be written as BCX plus YAB. Okay, I'm just stating these inequalities. I'm not yet sure, in fact, whether we'll use them or not. But these are some basic rank inequalities that exist, and it's just good to know. I'm not proving these because it will detract from getting to the core material of this course. But for now, I just want to state some of these basic results that are known about the rank. So specifically, I've highlighted two results. One to do with the product of matrices, the other to do with the sum of matrices, and then this more general result called the Frobenius inequality, which involves three matrices.
So just one correction, I think Silver's inequality is the first inequality that talked about the product. The rank of AB is constrained with.
That's right, actually. So let's correct that. So I think I have messed up my notes a little bit. So yeah. So let me maybe do the following. This thing doesn't have a name, so I'll just say rank of the sum A M by N. Of course, see, there's also a notational thing here. R to the M by N. Thanks, Chirag. So here the definitions of AB are different. Both are M by N matrices. Whereas here, A is of size M by K and B is of size K by N. Only then is AB actually defined. Then this is called the Sylvester. Okay, just one or two more properties. One is that rank of A is unchanged by left or right multiplication by a full rank matrix. Okay, you cannot decrease the rank, nor can you increase the rank by left or right multiplication. Of course, you cannot increase the rank. We've already seen that rank of AB is less than or equal to min of rank A and rank B. But you cannot decrease the rank by left or right multiplication by a full rank matrix. And another property, which is something I already alluded to when I talked about subadditivity, is that yes, go ahead, please.
Sir, full rank matrix means number of rows equal to number of columns equal to rank, right?
No. Full rank matrix. So let me clarify that here. So I actually said that in the previous class. So A in R to the M by N as full rank if rank of A is less than min of Mn,
Then it is rank deficient.
exactly. So A is said to be rank deficient. Okay. The other point I want to make is that any A belonging to R to the M by N of rank 1 can be written x A is equal to xy transpose, where x is in R to the M and y is in R to the N. So related to this, note that if I have x in R to the M and y in R to the N, and I construct a matrix xy transpose, it doesn't matter which x and which y I take. If x and y are non-zero, then xy transpose is always of rank 1. Okay. So one way to see that is when I do xy transpose, x is a column vector, and by multiplying by y transpose, all I'm doing is repeating this column x multiple times, in fact n times, and each time I'm multiplying that column by the corresponding coefficient of y, and I'm putting them together as a matrix. So all the columns of A are linearly dependent, and there is only one linearly independent column. Okay. Now, the next thing I want to discuss is the inner product. But before that, this is a small digression of different representations of matrix multiplication, because this is also something that we will use later on. So there are 3 ways to view matrix multiplication.
Sir,
Yes.
will the range space of the above mentioned A is equal to range space span of X?
What do you think?
It will be equal to.
Yeah. So consider that you have an M by.
Then will it be equal to span of Y?
So every column of A is a scaled version of X. So the range space of A is basically the span of X.
If we write Y into X transpose, then it will be span of Y, right?
Correct.
Okay, sir.
So the range space of A transpose would be span of Y. So suppose you write C as A times B, where A is a matrix of size m by k and B is a matrix of size k by n. Then one way to view this is in terms of an inner product, which we have seen in one of the previous classes already, but we'll also formally define it in a few minutes. But inner product. So suppose I have A and B as vectors of the same length. Then the inner product is defined as A transpose B, which is just a real number. Okay, then if I consider AI transpose.
Sir?
Yeah.
So what is length of a vector?
Length of a vector is the number of elements in it.
Okay. So wouldn't it just be equal to the dimension?
Okay. You like dimension, I can write dimension.
Okay, okay.
No, but you're right in that we will momentarily define length of a vector also. And so same dimension or size is what I really meant here. Okay, so suppose AI is the ith row of A and BI also in R power K is the jth column of A, jth column of B.
Hello, sir.
Yeah, please go ahead.
Sir, what is VECS in bracket ident?
Vectors.
Vectors. Okay, sir.
So the ijth entry of the product AB is nothing but the inner product between the ith row of A and the jth column of B. So this is one way to view matrix multiplication. Every element of the product matrix is an inner product between a row of A and a column of B. The other representation is the column representation.
Sir, it should be sigma I transpose B there. Sigma
there is
should
no
be there.
summation here. Yeah, so there is no summation here. This is the inner product representation. So if I have two matrices and I'm taking their product, recall that if you want the 1,1th element of their product, you have to take the first row of this matrix, first column of this matrix, take their inner product, and that gives you the 1,1th element of this product. If I want the say 2,3th entry of this product matrix, then I must take the second row and then the third column. So there's one more here, and then I take the inner product of the two red vectors, and that gives me the 2,3th entry. So this is called the inner product representation. The other thing is the column representation. So Cj, if I define to be the jth column of C, okay, which is going to be in R to the M, then this is equal to summation I equal to 1 to K AI B ij. This is true for j equal to 1, 2 up to n. Okay, so each column of this matrix C is a linear combination of the columns of A. And what are the coefficients? They are given by Bij. The jth column of B gives you the coefficients of the linear combination that will form the jth column of C. Okay, so it's a linear combination. I repeat, it's a linear combination of the columns of A with the coefficients given by the jth column of B. And the third is the outer product representation. So we can also write the entire matrix C. So we are going from small to big. Here we looked at how to write an ijth entry of C, a single entry of C. This is for getting you an entire column of C. And this is a representation which will give you the entire matrix C itself. This is equal to summation K, no, I'll write it in terms of I equal to 1 through K, AI, BI transpose. So this is the ith column of A. And this is the ith row of B. Now since A is of size m by k, the ith column of A is of size m by 1 and the ith row of B is of size 1 by n. So when I take this outer product, I'll get an m by n matrix. And so the matrix C is the sum of k rank 1 matrices of size m by n. Okay, so now we move on to the inner product.
Sir, what is AI and B? Like column representation.
Sorry, I didn't understand your question.
Sir, in column representation session, what is AI in that summation, inside summation?
Okay. These are the columns of A. And AI is the ith column of A.
Then that summation
The
runs
same
from
column.
1 to K or 1 to M? Sir,
1, 2. Okay, so maybe just hold on one second. A is of size m by k. So A has k columns. Yeah, so the summation goes from 1 to k. So what is the question? There are k columns in the matrix A. A is of size m by k. A1 is the first column. A2 is the second column. AK is the kth column.
okay, sir, now I got it.
Does it mean the jth column of C belongs to R of M?
The jth column of C is in R to the M. Yes.
But
Every
here it
column
is
of C
written
is in Rm. C is of size m
in
by
column.
n.
Yes, sir. But it is written R to the power of M there.
R to the power?
M in column representations.
No, Cj is the jth column of C. It is in R to the M.
M.
R to the N.
Okay, thank you.
So you are right. Yeah, each column is in R to the M. Okay, and there are n such columns. Is it clear?
Yes, sir. Yes, sir.
Yeah, these things are a little tricky. It's good to think about it independently. Yeah, but sometimes it can be a little bit confusing. So the usual inner product. So given two vectors x in c to the n and y in c to the n. So I'm using complex vectors here because it's just the more general definition. So the inner product between x and y is written like this, and it is equal to y Hermitian x, or it is defined as y Hermitian x, and this is also called the dot product. So Hermitian is nothing but the conjugate transpose. So you take the transpose of y and then you take the complex conjugate of every entry. That is y Hermitian. Y Hermitian inner product with or dot product with x is defined to be the inner product between x and y. There are other definitions possible, but we'll revisit that later in the course. But this definition here, it satisfies two properties that I can immediately tell you. The first is that if I take alpha x1 plus beta x2 inner product with y, this is going to be equal to alpha inner product of x1 and y plus beta inner product of x2 with y. But if I take the inner product between x and alpha y1 plus beta y2, what will I get?
A conjugate.
X y1 plus beta star x y2. So it is linear in the first argument, okay, and it is conjugate linear in the second argument. Now we can immediately define orthogonality. A set of vectors are said to be orthogonal if every pair of vectors in the set are orthogonal. Okay, so you take any two vectors, you take their inner product, you get 0. Then we say that if that happens for every pair of vectors in the set, we say that the set of vectors are orthogonal. Now, one inequality, very famous one, related to the inner product is what? There's one very famous inequality associated with the inner product.
Cauchy-Schwarz.
Exactly. So before I put down the Cauchy-Schwarz inequality, let me just say one small thing. If I take square root of the inner product of x with itself, this is called the Euclidean length. of x in c to the n. Okay, and also it's also denoted by norm of x2. Now, if the inner product of x with itself is 1, then the vector x is said to be normalized, or that x is a unit vector. So basically, if I take any vector x in c to the n, then x over square root of the inner product of x with itself is a unit vector pointing in the direction of x.
Sir?
Yes, please.
So what is the subscript 2 in the above statement? What does it mean?
Can you take a guess?
Sir, the inner product of two quantities?
No.
The square root, it is square root, right?
Yeah, no, not that. So the point is that if you look at what this thing is doing, it's taking every entry of x, taking the mod square of it, adding that up across the entries, and then you're finally taking a square root. Okay, because you're taking the square of each of the entries and then eventually taking the square root, it is denoted by norm x2. So if, I mean, since you asked the question, I'll say that norm x p is going to be equal to okay, so this is a definition of the what is called the p norm of x. It's also known as the LP norm, and it turns out it is a norm for p greater than or equal to 1. Okay, but I haven't defined what a norm is. So for now, you take it on faith that if for any p greater than or equal to 1, I can define norm xp to be this quantity here, and it actually is a norm. So we'll study that later. So there are other kinds of inner products and norms that you can define, which we will study later. But now I'm ready to state the Cauchy-Schwarz inequality.
Sir, I have a question. We cannot define zero norm, right? Because
so you can define norm xp for p p less than 1, and you can take p equals 0. You can even take negative p. But for p less than 1, this norm xp will not be a norm. And so I don't want to get into the details right now because I haven't defined norm yet. We will define it in 1 or 2 classes, and then we can discuss these properties. But for now, I just want to relate it to this. Somebody asked me why it is norm x2 here. And so I'm just answering that it is actually coming from a more general definition of the length of a vector, which can be defined like this. And this is a valid definition of the length of a vector for p greater than or equal to 1. So let's not worry about what happens when p is less than 1 or equal to 0 or even negative just for the moment. We'll come back to that point later.
Okay, sir. Thank you, sir.
So the Cauchy-Schwarz inequality simply says that the inner product between y and x in magnitude is less than or equal to the inner product between x and itself power half times the inner product between y and itself power half. And with equality, if and only if x and y are linearly dependent. Basically, they point in the same direction. So the proof is very quick, so I'm just going to, in the dying minutes of this class, run through the proof. All you do is you start with noting that x inner product with x is always greater than or equal to 0 with equality if and only if x equals 0. Okay, as I wrote it here, you can see that the inner product of x with itself is the sum of the squares of the entries of x power 1 by 2. And so if this equals 0, the sum of the squares of the entries is 0, which is only possible if every one of these entries is 0. Because they're all non-negative quantities. So now we'll take this x minus lambda y inner product with itself. And this is because I'm taking the inner product of a vector with itself, and lambda is some scalar here. And since it's the inner product of a vector with itself, this is always greater than or equal to 0 with equality only if and only if x minus lambda y equals 0. So from this you can already see that the equality condition will only be satisfied if x equals lambda y, so that this difference is 0, which means that x and y are linearly dependent. And this is true for every x, y belonging to c to the n and lambda belonging to c. So we just expand the left hand side, and if you expand it out, you will see you just have to take this Hermitian times this and expand it out. You will see that this is equal to x Hermitian x minus lambda x Hermitian y minus lambda star y Hermitian x plus mod lambda square y Hermitian y. Okay. Now if y equals 0, then this inequality is trivially satisfied. Yx inner product is less than or equal to this times this. If y equals 0, the left hand side is 0, the right hand side is also equal to 0. And so this inequality is trivially satisfied. So I'll just say y equal to 0, the Cauchy-Schwarz is trivially satisfied. So assume y is not equal to 0, and in that case I can choose lambda equal to y Hermitian x over y Hermitian y, which is equal to the inner product between x and y divided by the inner product between y and y. If I substitute this value of lambda here, you see that I get y Hermitian x times x Hermitian y, which is the same as mod of x Hermitian y squared divided by y Hermitian y. And this term is also y Hermitian, the conjugate of y Hermitian x is nothing but x Hermitian y times y Hermitian x divided by y Hermitian y. So I'll just, and in this last case, I get mod of y Hermitian x squared, and one of the y Hermitian y's will cancel, and I'll be left with y Hermitian y in the denominator. So just writing it out, the above becomes x Hermitian x, which stays as it is, minus x Hermitian y squared over y Hermitian y minus x Hermitian y squared over y Hamilton y plus x Hamilton y squared divided by y Hamilton y. So things I've used here, so this is greater than or equal to 0, and these two terms obviously cancel, and so which implies that x Hamilton x minus x Hamilton y squared over y Hamilton y is greater than or equal to 0, from which the inequality follows. All I have to do is to take this to the other side, bring y Hamilton y to the top, and then take the square root throughout. So I used a couple of things here. One is that x Hamilton y complex conjugate equals y Hamilton x. Okay, this is one. I guess this is the only side result that I use, and you can see that you can. This is not difficult to see, so you can see that this is true. Just write out what it is, then. So just keep in mind that y Hamilton is equal to y transpose complex conjugate. Okay, so that's the proof of this inequality. Okay, we'll stop here. Are there any quick questions?
Sir, hello. Audible, sir? Hello.